Alright, so in this video we're going to try to prove the fundamental theorem of calculus, or at least one of them. So the diagram I set up here, it looks like there's a lot to take a look at, but really we can unpack this piece by piece. So let's take a look at the first thing. The maroon color is from a to x and it's shaded like this, and that's the area. So that's the area under a curve from a to x, and that's represented by a function g of x. Right now we don't know what that function is, but we're claiming g of x is equivalent to the definite integral from a to x of f of x. Now this black curve here is some function f of x. I mean, it's some polynomial. You know, it could be something like x cubed plus x squared plus 5x minus 1, right? It's what that's so basically you plug in a number for x, you get a number for f of x, which is y, right? You plug in a number on one of these from here, you get this number on the y-axis. Okay, so we know this is what we're claiming, and we're going to try to prove this, that in fact the area function is equivalent to the antiderivative of f of x, and you can denote the antiderivative by this notation here. Okay, so now I have something else drawn. It's kind of hard to see, but you have a here, and then you have x plus h. And the area from a to x plus h is this blue, and that's denoted by g of x plus h. Remember, now this isn't, don't let this be daunting or confusing. We're literally just plugging in numbers on the x-axis. We're plugging in x, which is this point here, x plus h here. So again, this area function is going to be denoted by a, our starting point, to x plus h, all the way here on the x-axis. And it's going to be, so that's going to give us the area from this a to this point. Okay. So now what we're going to end up doing is, let's see, we're going to take g of x plus h minus g of x, right? And that's going to give us the integral from, or, so what would that give us? Let's think about that. That would give us this area right here, right? So g of x plus h, again, remember, it's the area from a to x plus h. This entire, all of this area right here. Now, the area of g of x is just from here, a to x, so it's just this area right here. So if we subtract the two, we're going to get, it's kind of like if you walked 10 steps, right? And then you walked 9. 10 minus 9 is just going to give you 1. Well, if you walk x plus h steps, you know, initially, and then you walk x, if you subtract the two distances, you're going to get x plus h minus x, it's going to just leave you h, right? So here, this length can be denoted by h. Okay, so g of x plus h minus g of x is roughly equivalent to h times f of x, right? Because this is the base h, and if you look really close, if you can approximate it, this is a rectangle, right? So base times height. Height is just some point on this curve, f of x. We don't know what the point is. That's why we leave it in vague terms as f of x, because it's some point. It responds to some y value, some y height. If you plug in a value here from the x-axis, you get some y value. So this is rough. This is a close approximation. Okay, so now we're going to divide both sides by h. So divide by h, h's cancel out. Now we have this. This at first glance should be the derivative, right? This is what we recognize as the derivative. So what is this telling us? This is interesting. So it's saying the derivative of the area function is equivalent to the curve, the function that's representing the curve, right? This is a derivative. This is simply the derivative. G of x plus h minus g of x all over h, as h goes to 0 is equivalent to, and as h goes